Hi everyone. So welcome to the last video on Chapter 6 material. So we're picking up right where we left off from our second Chapter 6 video to just talk about some final skills. And actually, before we do that, let's back up and let's visualize this binomial distribution. In the previous example, we were talking about watching an NBA player shoot 20 free throws. We talked about how each free throw represents a Bernoulli trial, because each trial will either be a success or a failure, and how each Bernoulli trial has a 70% probability of success, and how we can use that to come up with things like the mean of this discrete random variable, the median, the mode, the variance, the standard deviation, all these things that we normally talk about for data sets or for random processes. And we also talked about how to use the binomial probability mass function and cumulative distribution function to answer important questions about probabilities when we have this sort of setup. So it's nice to know the mechanics and how to evaluate these things, but I think it's also important to be able to see what a binomial distribution looks like. And so again, let's take this exact example and just put it into Desmos and look at what happens. So here is, in red, a binomial distribution in the Desmos online graphing calculator. But we're looking for a distribution with 20 Bernoulli trials. So over here, I'll let n equal 20. And then I want a probability of success to be 0.7 for each of the Bernoulli trials. And so this red lump over here, this represents the binomial distribution. So where x is equal to 10, you can see that the probability is 0.03. When x is equal to 9, the probability is 0.01. I guess basically what I'm trying to say is that the value of this function at each one of these flat little parts here, that value is the binomial distribution probability mass function evaluated at each of these numbers, right? So the probability is relatively low, 0.0008, that you're actually going to get 20 out of 20 free throws. And it turns out that the highest probability is that you'll shoot 14 free throws, right? With a probability of 19.16%. And so that's why 14 is the mode of this distribution. And we also found that 14 was the mean and the median as well. But in any case, this is what it looks like where the height of each of these bars, represents the probability that the outcome for your binomially distributed random variable will be the exact value that's shown along the horizontal axis, right? So what's the probability that we get exactly 15? Well, it's the height of this bar, which is 0.1789. This is a way of visualizing the binomial distribution. And it's nice, I'll probably post a link to this Desmos tool so that you can mess around with it and you can get to it on the Canvas course homepage. But if we change the value of n, the number of Bernoulli trials, that obviously changes the shape of the binomial distribution. If I change p, the probability of success of one of the Bernoulli trials, and decrease the probability of success, you can see that it becomes more likely that we'll have a lower value for our binomial random variable. If I make the Bernoulli trials more likely to be successful, you'll see that makes the probabilities for the larger end of the binomial random variable to be the most likely outcomes. So anyways, neat little binomial distribution. What I want to point out next is that while this binomial distribution is not the same thing as the normal distribution that we've discussed in previous chapters, it's kind of like the normal distribution. So while it's not the same, and there's big important differences, right? But the binomial distribution describes a particular type of discrete random variable, where your random variable can only take on discrete values like 1, 2, 3, 4, 5, 6. A normal distribution describes a type of continuous random variable, where you can have outcomes like 1.5 and 7.159 But what I want to point out now is that whenever the variance of the binomial distribution is greater than 10, the binomial distribution does start to kind of look like the normal distribution. So remember, n times p times 1 minus p, that's just the formula for the variance of the binomial distribution. And so when that's greater than about 10, we say that the binomial distribution starts to look like the normal. So what I mean by that is if p is somewhere in the middle, like p is around 0.5, and if n is large enough, this red curve looks a whole lot like the normal curve if I let the mean of the normal curve be n times p, and the standard deviation of the normal curve be the square root of n times p times 1 minus p. And then what I'm going to do here is just put a normal curve right on top of that red curve. And so in blue, what you're looking at, that curve in blue, let me take away the red curve. That's the normal distribution approximation to this red binomial distribution. And you can see that they actually match each other very, very well whenever n is large and p is about half. So we can approximate the binomial distribution using a normal distribution with the same mean and the same standard deviation. Now, this approximation does fail if n is a small number, like if I let n be 6, let's say, and if p is close to 1. You see how it's kind of doesn't match nearly as well for like this point right here, or for this point out here. Or if p is really close to 0, again, it doesn't seem to match very well if you have small values for n and extreme values for p. So like what we see right now, whenever I have n equals 11 and p equals 0.06, in red, that binomial distribution is right skewed because the mode is 0 and everything else in the distribution happens to the right. But the normal distribution, this blue curve, is always symmetric. The normal distribution can never be right skewed or left skewed, and so you know that this is not a good approximation here. But again, just to maybe say this too many times, but to really emphasize the point, as long as p is somewhere in the middle and n is sufficiently large, we can create an approximation where the normal curve can approximate a binomial distribution like you see happening right here. Okay, so again, in that normal approximation to the binomial distribution, the population mean is n times p, the number of Bernoulli trials times the probability of success of one of those Bernoulli trials. And the population standard deviation is going to be the square root of np times 1 minus p. It's important that p is somewhere in the middle because if p is too close to 1, then this 1 minus p term will be really, really small. And if p is too close to 0, then that p factor will be very small. And so in either of those extreme cases of your p, you get a really low variance. And we want variance to be large if we want to approximate that distribution with the normal curve. Okay, so the last skill we're going to discuss is what we call finding unusual results. So we say that the result of a binomial experiment is unusual if it falls outside of 95% of the predicted outcomes. And so what I mean is the most likely 95% of the predicted outcomes or the possible outcomes. That's what we consider to be unusual. So this image is something I pulled out of a video from a much earlier chapter in this course, but you maybe remember this. The purpose of this graphic is to illustrate what we call the empirical rule, which is to say that within plus or minus 1 standard deviation, that's where 68% of the expected data lies for a normally distributed random variable. And within plus or minus 2 standard deviations, we expect to find 95.4% of our measurements. And then within plus or minus 3 standard deviations, we expect to find 99.73%. So when I tell you that we say that results are unusual when they fall outside of the 95% of the most likely outcomes, what I'm saying is anything out here in this area outside of plus or minus 2 standard deviations of the mean, these are unlikely according to our definition. And you can see that they're unlikely because there's not a whole lot of area underneath this curve here. Right? Not very many of these measurements are falling in these extreme regions that fall outside of plus or minus 2 standard deviations around the mean. So here's one example that we'll use to wrap up this section. One example of finding unusual results, or not. And we'll see how it goes. We know that the incidence rate of autism among the whole population in the US is about 1.5%. So like 1.5% of individuals have autism, let's say. Now, if you come across a city that has 10,000 children between the ages of 5 and 15, and you look at this, population of children in the city, and you find that 105 are diagnosed with autism, we might ask, is this an unusual result? And this is probably something that health professionals are actually interested in, right? Because if you find, that one particular city or town has an incidence rate of, any kind of diagnosis like this that's much lower than the overall incidence rate, you probably suspect that there's a lot of cases that are going undiagnosed and that maybe there needs to be, more attention paid to this area in terms of this kind of diagnosis, maybe getting more doctors out there. And if you find an incidence rate that's much, much higher than the, population at large, then I guess what that means is that, there could be maybe some kind of issue going on that's actually causing additional diagnoses, or maybe the doctors in that place are using a lower standard for diagnosis, right? And so in any case, you want to find unusual results, and you want to, use that to dig deeper and investigate what's happening, right? But for this example, let's use our rule that we just talked about to determine if this particular result, 105 out of 10,000, is that unusual or not? So in this case, we're talking about a binomial distribution, and maybe it's not super obvious, but each child represents a Bernoulli trial. And I say that each child is a Bernoulli trial because for each child, either they are or are not diagnosed with autism. And so this is sort of a success or failure type of situation. There's only 2 possible outcomes, and that's the definition of a Bernoulli trial. So then the number of children who are diagnosed, that's a binomially distributed random variable because it's the sum of, the outcomes of a bunch of Bernoulli trials. So the number of Bernoulli trials we have in this case would be 10,000. And using our overall population incidence rate, we can determine that the probability that one of these Bernoulli trials will come up with a diagnosis, that is 0.015 for that probability. So we have our n and we have our p, so that tells me I have a fully specified binomial distribution. And for a binomial distribution, remember that the mean is n times p, and the standard deviation is going to be, well, I'll write out the variance as n times p times 1 minus p And then we remember that the standard deviation is just the square root of the variance. So putting some numbers to this, the mean is going to be 10,000 times 0.015. And so, let's see, 4 zeros borrowed from the 10,000 makes this 150 as my mean. So I really expect, remember mean is expected value, I expect to find 150 diagnoses among a population of 10,000 children, right? This is what my expected value is. Now, just because the 105 diagnoses is not exactly 150, that doesn't make it an unusual result, because, you can have, give or take a few from your expected value, but, you just can't vary too far away from the expected value. So to determine how far is too far, that's where we look over at our variance, which will be 10,000 times 0.015 times 1 minus 0.015. And I will get out the calculator for that one. And like I just said, 10,000 times 0.015 times, open parentheses, 1 minus 0.015, close parentheses. This is my variance. It's 148. Well, let me write variance we found is 148. And so the standard deviation is, of course, the square root of the variance. So I can take the answer I just got and raise it to the power 0.5 to take the square root. And so my standard deviation is going to be 12.1 or 12.2. So now the question is this an unusual result, right? And we've just talked about how we're considering it an unlikely or unusual result if it lies outside of 2 standard deviations away from the mean. And so 105 is less than my mean of 150. So let's try to take 150 minus 2 standard deviations. So we'll do 150 minus 2 times 12.2. And that's going to be 125.6. What that means is anything less than 125.6 qualifies as an unlikely or unusual result. So in this case, yeah, finding only 105 diagnoses among 10,000 children, this is unlikely, or this is unusual. And so that's how you'd answer this type of question. There's one more thing that I forgot to mention that's still very important, is if you want to use this kind of reasoning in this type of problem, you need to have, you need to make sure that the normal approximation works for your binomial distribution. And like I said in a previous slide, we say that the binomial looks enough like the normal distribution if the variance of the binomial distribution is greater than 10. And if it's not greater than 10, technically you cannot use this line of reasoning, because this sort of assumes that we're talking about a symmetric normal-like curve when we use the plus or minus 2 standard deviations as our criterion. So let's now that we've already worked the problem, let's go back and just make sure that what we did is valid. And what I mean by that is, what was our variance, and is it greater than 10? And actually, we've calculated the variance, and we found our variance to be 148, and so that's well over 10. So this binomial distribution is normal enough to treat it as if it was a normal distribution. So this sort of reasoning does work. All right, y'all have a great week.